So in the previous video, what we did was we showed if we had an insulated rod, so in terms of a picture, something like this, and we were interested, suppose it had some initial starting temperature, which we'll probably imagine is 0, and then you put it in thermal contact with these two heat sources. How does the temperature change? What we showed was that the temperature would, well, we didn't completely show all this, but the temperature will increase from 0 up to this steady state temperature. Okay, and the question is, how does the temperature change in time from 0 up to this steady state? And we showed that by considering how would you get a change in temperature? Well, if you had a little element of the rod, if you had a net change in heat energy, that would give you a change in temperature. And by considering that, we derive this little equation here. Okay, now what we want to do, remember we're doing numerical methods, is approximate solutions of this. Okay, so now what we have to do is understand the way we're setting this up. Okay, and we're looking at the temperature at a point on the rod as a function of time. So the temperature is a function of two variables, the distance along the rod and the time. Now that means that the domain, as it were, on which the function is defined is two-dimensional. So we'll do the schematic here. Okay, so first of all, the amount of what we're going to do is we're going to do the time in the y-axis. It's a little bit unusual, but once you get your head around it, it's not too bad. So this is the time dimension. Now we don't actually know how long we're going to run it for, but what we're going to say is that we know that if we wait long enough, the temperature will eventually reach equilibrium. So we're going to keep running this until the difference in temperature at each point that we're looking at, between the difference in that and the steady state, is small. And we know how to find the steady state temperature. That's actually not that difficult. It's just a line after all. We showed this in the previous thing. So that is open-ended. Now what isn't open-ended is the x direction, because x just goes as far as the length of the rod. Okay, so this, I have it open-ended here, but it's not actually open-ended because it only goes as far as here. This is the length of the rod. Now we do have temperatures at this point and at this point. These are the, now I think in any question I do, they're going to be fixed. So everywhere along this thing, so temperature is equal to, I think we'll call it, say, T1. That may or may not be a good notation. At x equal to L for all time. Okay, and similar story, the temperature at x equal to 0. So write this down. So the temperature is equal to temperature 0 at x equal to 0 for all t. Right, now what we're going to do is we're going to chop the rod up into a couple of pieces now. I'll probably do it into like 5 pieces here or something like that. So say T1, T2, T3, T4. Now what we're doing is we can do this for plates and boxes as well, but we're just going to focus on rods. Okay, so here in terms of notation, let's say, of course these are going to be little delta x's. So we could call this, if we wanted, we could call this x1, x2, x3, x4. And we might write down here that xi is equal to I times delta x. So for example, x2 is 2 delta x's. Now, so that we chop the rod up, then we chop the time up. Now, we don't know the end time, so it's a different kind of a thing. So basically we just choose a delta t. Now usually I'm thinking 0.1 of a second. Okay, so I'll give myself plenty of space here. So that'll be 1 second. And another second, say something like this. And maybe a bit finer. This isn't my best ever work, but it should be okay. Yeah, these should be equidistant. Okay. We'll do one. Okay. Dot dot dot. Do one more. Well, we'll just exaggerate these. Okay, so let's say, let's just say in case you're looking back, this is not the scale. These all should be the same. Okay, so this is time 1, which is equal to 1 delta t. Time 2 is equal to 2 delta t. Time 3 is equal to 3 delta t. And actually the way I'm going to do it is, oh yeah, I want to do dot dot dot, so we'll do the dot 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 here. So imagine there's loads of them. This really means it's not scale. And then I think I want this term to be TL equal to L times delta t. And then I'm going to, I think, imagine that this is Ti. Because I need to generalize this to write down a formula. So this will be like Xi, this particular one I'm thinking about. Okay, so what we're going to do, and hopefully this will make some sense, is we are going to, okay, we've got a differential equation, a partial differential equation, and no different to Laplace's equation. What we're going to do is we're going to simplify the equation. We're going to use finite differences to simplify this. But the thing is, we've got changes in distance, x, and also changes in time. So in terms of finite differences, where you're talking next, current, previous with respect to x, and next and previous with respect to t are different things. So the following thing I want you to get an understanding of. So we're going to have a point here, a point here, and a point here. And these 3 temperatures are going to come together to produce this temperature here. Now, this is what we're going to see. Now, I'm going to start writing something down now that hopefully we can understand. So this, so instead of saying it's x3, let's say it's xi. So this is the temperature at the point I at time L. So it's kind of saying, okay, what is TIL? It's an approximation of the temperature on this distance along the rod at this time. This one is 1 along the x. So instead of I, it'll be I plus 1. So this means the temperature here, but at the same time. And this is at the previous temperature with respect to x, so this goes back to T minus 1. Now what I want you to see is with these 3 temperatures, which is just at this time, the temperature at this point, this point, this point, they're all at the same time. Now what we get up here is the temperature at the same point at the next time. And what we're going to do is we're going to write the heat equation with an equation where you get this temperature in terms of these 3. And if you think about it, then that allows you to do everything. So what you're going to have is the temperature along here is fixed, the temperature along here is fixed. You're going to have an initial temperature distribution, which will usually be 0. And you're going to have, say, this point, this point, this point, this point, and this temperature is going to depend on these 3. This temperature is going to depend on these 3. This is going to depend on these 3. And this is going to depend on these 3. So given the temperature at a certain time, you can calculate the temperature at the next time. And this is what is going on here. Now, this picture is probably the most important to understand these 3 things here. Okay. So what we need is we need finite difference approximations for the second and the first derivatives. Now I haven't seemed to have left much space here. So I'm going to take an additional scrap of paper. And I'm looking at this heat equation down here. Grabbing my paper there, sorry. So what we do is we look up you can look up a formula kind of that I'll be giving to you. So the kind of formula that we'd be looking at is that the second derivative is a finite difference approximation, at a certain point x equal to xi is equal to, well, not equal to, approximately equal to. So this, in any assessment, this is a formula that you'd have. It is the value of y at the next point along the x minus twice the value of y at the current point plus the value of y at the previous point. I'm going to write this in a slightly different notation actually, divided by the distance between the x's squared. This could be written as, and this would be equals, this you could call yi plus 1, the next y value, minus twice yi, as twice the current value, plus yi minus 1, the previous value, divided by delta x squared. And you could even go a little bit more extreme than this, and we could say next minus twice current plus previous divided by, well, let's keep the delta x squared. Okay, and what we're going to do is we're going to approximate this second derivative using this thing at a particular point and at a fixed time. Okay, so next minus twice current plus previous. Now remember, this will be given to you in any assessment. Okay, so let's go. The second derivative, now it's multiplied by k, so I'm going to throw the k in there. And I'm talking about at this point. So the thing I just taken away, so next. Now this one, the derivative is with respect to x. The derivative here is with respect to x, so it must be the next point. So basically what I'm saying is that I'm writing this differential equation at this point. That's what I'm referring to here. So next is this thing. Now it's next in terms of x, I plus 1L, minus twice the current in terms of x is minus twice this, plus the previous, which is this, over twice, over delta x squared. So this is, what am I doing? Slow it down. I'm approximating this second derivative using finite differences. So a second derivative at a point is approximately the next value with respect to x minus twice the current plus the previous divided by delta x squared. This is exactly what I have here. I have the next with respect to x minus twice the current plus the previous divided by delta x squared. Now if I want, I can talk about a similar finite difference approximation to a derivative, dy dx, a first derivative. So this would be approximately, again we can go with something like y of xi plus 1 minus y of xi over delta x. This is an approximation. It gets more and more accurate when delta x gets smaller. Now this is, in another context I remember you want to be able to do derivative as just rise over run, and in particular you could do this first derivative like that. The rise would be the difference between these temperatures and the run would be delta T. That's fine. If you can do that, I think that's the best way of doing it. Alternative, let's look at this again another way. This would be the next value of y minus the current value of y divided by delta x. And this, of course, is the same as, so the next value, so the derivative at a particular point is approximately equal to the next value minus the current value over delta x. And that's, we're going to approximate this with. Now here, what's changing is time. So it'll be next in terms of time, and the change in x will be a change in time, which we're saying is delta t. So this is equal to next minus current. So the next in terms of time is this thing. Minus the current is just TIL divided by the change, and the change here is delta t. So this is what we got. And the interesting thing about this is we have the temperature at this point at the next time in terms of these three. So this is the only one at the next time, and therefore we can do it. And actually this is a place where people go a bit bonkers, because they you do all the hard work. So you'll have to do this. This is the hard work. And then what you do is solve for this. So people's algebra lets them down. We'll be a little bit more careful. So you want to multiply both sides by delta t, and I'm going to swap the two equations around. And if I do that, so multiply both sides by delta t, and if I swap around, so this is now the left-hand side. So multiplying this by delta t, there'll be no delta t. I'll have t I L plus 1 minus t I L. Multiplying both sides by delta t, I end up with k times delta t over delta x squared, and then just all this yoke. Ti plus 1l minus ti L plus ti minus 1l, and then I just have to add this to both sides. So it actually looks a little bit like an Euler method, because what you have is the next value with respect to time is equal to the previous value. Actually, I never thought of doing this. You can actually do this directly using Euler's method, because what does Euler say? It says the next value is equal to the previous value plus the step size. Now the step size here is delta t, so I'll just draw this slightly differently, times the derivative. And look at this is the derivative, so you get this thing. I never thought of that before. So this is pretty much Euler's rule. Just looks a bit funky. It also suggests that it's not going to be very accurate, which isn't great. There's more accurate ways of doing this, but I don't bother. Okay, so you get the temperature at a point at the next time in terms of the temperature at the previous times. There's a few things that we want to say here. The first is, if we are thinking about Euler's method, there's a suspicion that if this is big, there's going to be a problem. So this must be kept small. We'll talk about that a little bit later. Because obviously if that's big, you've got a big step size, you're going to have errors. The second thing to note is in terms of VBA, here you've got new values and these are all old values. And as you go across, what's going to happen is if you write this in VBA code, you're going to calculate new values. That means that you're going to have to, in terms of VBA, we may as well write this down, either take the old values from the worksheet. So what I mean by that is, like, so this would be like, say this would be like the new temperature, say T1, and this would have to be like cells int row, whatever column T1 is in. This is going to be a constant because delta x and delta t be given to you. This would be like cells int row the next column on, so it'll be like whatever +1. Similar story going the whole way across. So you could take them from the worksheet, or else I think what a lot of people seem to be doing is define t old variable. And you can do it like that. Now, rather than do a little example of actually in my opinion, getting from here to here is the difficult part. We might just focus a little bit on this, that this must be kept small. Now, it's not as simple as it looks, because basically, if you make delta x to be small, which you know you need to chop up the reason that, okay, you need to chop up delta x to be small to make this approximation accurate, to make the derivation accurate. But if you make delta x too small, what happens when you divide by, and particularly if you square, what happens when you divide by a small number, you get a big number. So there's an issue here, is that if delta x is to be small, then to keep this whole thing small, delta t must get small as well. And of course, there's only two O's and two. And of course, what that means is if you've got a smaller delta x to make things more accurate, you have to get a smaller delta t to keep things accurate. You're getting loads and loads of calculations. So it's a little bit difficult to do this accurately. Like, similar story. Now, it's okay to make delta t small, I think. But then, like you've got loads of calculations, so it's a little bit tricky. Now we're going to talk about this specifically, I think. What you do, okay, once you derive this, my recommendation is, you'll probably have 3 or 4 internal nodes. You'd use arrays, of course, if you want to have more points that you're looking at the temperature. But you write this equation for each of the nodes. That's probably what we'll see what I do actually in the example. Now let's just look at this. So this thing we call, I think on the next page, this thing is called lambda. And it's very important that this is kept small. Because actually, what can happen, and I'm not going to prove it, I'm just going to believe what the book tells me, is that if this is big, you get serious problems. You get answers that are nonsense. You can also get oscillating behavior. Like what you expect to see is when you do this is that the temperatures are initially say 0 and that they rise up to that. And that's what happens in the real world. If that lambda is not big enough, I think you can get like crazy things happening, like the temperature going from 0 up to 100 down to minus 200 up to 400. That's obviously nonsense, and that's bad enough. No, that's very bad. So that wouldn't be that's unstable and it's not converging. The other thing you can get is oscillation. So the temperature might go from 0, say, to 50 to 40 to 46 so it's getting closer to the equilibrium solution, but not in a realistic way. Like in the real world, what's going to happen is the temperature is going to rise up. It's not going to oscillate. So you have to get this lambda thing small enough to avoid that happening. Okay, so let's see, we got this equation can be written for all the interior points in the node. I think this is probably what I'll do in the example in the next video. It then provides what's called an explicit method to compute values each node for a future time based on the present nodes. Okay, this lambda must be kept small, ideally less than a quarter. So you want it to converge. Convergence basically means that it gets closer to the equilibrium, and I think that is basically the same as stability, but I'm not too sure. Oscillations, so you can have oscillations, but for it to converge and be stable. I'm not 100% sure, but I think these things are the same. So to make it converge without oscillations, you've lambda less than a quarter. I think if you've lambda less than a half, you're guaranteed the convergence, but there may be oscillations. Okay, now we'll do this example in the next thing. There's a small comment somewhere down here. Okay, sorry, these are different things. So stability is what I was thinking of convergence. So convergence means that it's kind of a more complicated thing, that basically that if you make the delta x and the delta t be small, that this converges to the exact answer. And that doesn't mean the exact steady state temperature, because it's actually guaranteed to do that as long as it's stable, but that the temperatures that you find on the way up, that these are accurate as well. That's what the convergence is about. Stability is that the temperatures go to the steady state. You need that. And then the no oscillations we've discussed already. So what have we got here? So convergence means that as delta x and delta t get small, now you see you can't make delta x really small without making delta t small, because what will happen is that if delta x is really small, then you're dividing by a really, really small thing, you get a big number. So you can't just make delta x really, really small. You can't do that. If you make delta x small and delta t small, then what it's saying is that not only you're not going to get problems with oscillations, but that the temperatures that you're calculating, the transient temperatures, that they're accurate. Stability means that the errors are okay. So stability is about, as far as I'm concerned, stable means that if you keep running it, it doesn't get bigger and bigger and bigger. It gets closer and closer and closer to the steady state. That's what you want. And then the oscillations we've mentioned already. Now, one of the things that's interesting, and it's just a small remark, if you've been doing the Jacobi method for the temperature on a plate, now most of us have been doing Gauss-Seidel, but if you do Jacobi method, or even if you do Gauss-Seidel, you see the temperatures changing, and it's kind of tempting to think, oh, that's like the heat, the plate heating up. Now, if it's Gauss-Seidel, that's not the case. But if you actually do the heat equation with lambda equal to a half, let's see what you get. You get the T next. So this would be like T L plus 1, the next temperature, is equal to the previous temperature plus a half the next temperature minus twice the current temperature plus the previous temperature in terms of x here. Okay, and I think if you can rewrite this, you can actually get that this is equal to, so you get a cancellation here between these. You get next temperature plus, in terms of x, plus previous temperature in terms of x divided by 2. So it's saying the next temperature up here is the average of these two. And if you don't have a time element, it's saying that this is the average of these two. And that's exactly the Laplace equation, the steady state equation. Because remember, with Laplace on the plate, we said in steady state, the temperature at each point is the average of the adjacent nodes. So if you do Laplaces in one dimension just on the plate, the temperature will be the average of the two adjacents. So you got a comment here. So therefore, given a delta x equal to h grid, if the initial guesses for a Jacobi method are the same as the initial temperature distribution, then the Jacobi method calculates the heat distribution in certain intervals. So the dog is coming in there. So we get, we're saying lambda is equal to a half, and lambda is equal to, was it k? What was it? K delta t over delta x squared. And we're thinking here about a rod. So I multiply both sides by delta x squared, divide both sides by k, I get delta t is equal to delta x, don't really need the h, over 2k. So what this means is that if you do the Jacobi method, certainly with a rod, that the calculations, the intermediate calculations actually mean something. They are actually the rod heating up. I think you get the same story for Laplace's equation on a plate, in which case the intermediate temperatures you calculate actually mean something. Now the problem with Gauss-Seidel, you because you're not using all the old values, it's not the same as this heat equation, because say with Gauss-Seidel there's a mixture of next values and previous, so it's not actually, they mean anything. So it's just a small comment, not that important. It can happen that errors oscillate with such a large lambda. Setting lambda equal to a quarter ensures the solution will not oscillate. Here we said making the lambda small is a problem, because if you half delta x to get convergence, it increases the computation time by 8. Now we'll just show you one thing now to finish this lecture. The dog.